Simulated talk, who has questions? Okay, I actually have a few questions, and let's start from the physical question. When you said about interference on Josephson junction, I wanted to ask whether it's possible to observe, or are there such experiments for interference with vortex lattice? So if you apply magnetic field, you have a regular vortex lattice, maybe is there any attempts to try to realize interference of currents, of pair currents, of Josephson currents on the vortex lattice, to use it as a grating, for example?
Yeah, it has been done. This grating, I mean, it was the next idea. It was done by, proposed maybe more than 10 years ago now by a German team. When you go to a young experiment, the next step is to go to a grating. It means to put a lot of slots, and it is called a Kyiv. It's a superconducting quantum interference filter. So it's a network of Josephson junction in series or in parallel, or a combination. And you can do also this, you can use them at home.
But this is artificial.
It's artificial.
Artificial structure.
Yeah, it's an artificial
asking if maybe it's possible to apply magnetic field, and you have this regular vortices which acts as grating.
That's something else. I mean, you mean to induce the grating physically with vortices. Okay, but yeah, I didn't see anything about that. Yes, to
so I'm wondering why, because it's the scale is similar.
Yes, and indeed, this because of vortices network are very regular. So you need two things, I think. You need first probably to be, when you have these vortices, you are not too far from TC, usually. So probably sensitivity will be a bit degraded. But you need two effects. You need first to fabricate your grating electronically in some way, or thermally, and then to send the signals. Yes, why not? Never thought about that. I didn't see anything.
Okay.
May I ask a question? You told a lot about the superconducting electronics, but in which aspects the ordinary semiconductor electronic is still better than this? For instance, maybe it's a question of money, how to make those because silicon is easy right now, and we know this technology, and I know that in laboratory 3 nanometer transistors are already made.
Yeah.
So,
yes. So there are different things. It's not only indeed technological, because I'm sure semiconductors people have still a lot of, they will still do a lot of nice things, I'm quite sure. And I see where they go now. I mean, they will probably still use the superconductor for some parts, because I mean, supercomputers we don't see how to solve the problem otherwise. But for a lot of things, like this 6G or telecommunication thing, they will do a different kind of computing. It will be neuromorphic computing, in-memory computing. We try to reproduce the brain. What we do now is maybe because scientists are too Cartesians. We do things which are, how to say, very square, right? 1, 0, 1, 0, and when the circuit works, there is no mistake. It should work. But the brain doesn't work like that. We all make mistakes, right? So it means it's a very bad system in some ways, the brain, from this point of view. But at the same time, it works quite well, right? To solve some complex problems. So what is done in the brain is you don't have a memory and a computing. You don't have one hemisphere memory and the other one doing processing, right? It's just memory everywhere, some processing inside. So there are other solutions to do things, and maybe semiconductor will find some solution with that, but superconductor can do it as well. After, it's a matter of investment. Of course, semiconductors, it's billions of dollars of investment. They are not going to stop like that, but we can benefit from them. We can use our facilities. In the US, all these complex circuits Some of them are made in semiconductor facilities, in D-Waves that fabricate the circuit in semiconductor facilities. It's just a normal process. You just change copper by niobium, right? Of course, you need to have a few extra machines, but nothing is new on the microelectronics.
Okay, thank you. And another question. You've told that we gain the frequency better, 100 gigahertz, but the real performance is not measured only in frequencies. It's measured. It is a combination between frequency and transistor density. I believe. Does it? Maybe you told it, but I didn't get. Are there already some made solution, and can we compare them with the semiconductor technology for solving real world tasks? For instance, for calculating some PDE, just to come.
Yes, there are a few demonstrators. There are FFT transform system. There are microprocessors with integrated memory as well. So the first parameter, which is important, is energy delay. It's not frequency. You need to have the product of energy by delay, or energy divided by frequency. That's the first thing, for sure. Then we are better. After, the second problem is how many devices you have on a chip. 1 centimeter square, right? And here we have bigger devices, so of course there are less people to work. So even if we are all better, we have many less devices, so we cannot have complex functionality because we are too big. But the size, if you want the size, it's not, we can reduce. It's just because we didn't start to do the work, we didn't have money to do it, we can reduce the size. I mean, we can go to, now it's 200 nanometer, probably 90 nanometer is okay. At below, we'll see. We need to see how superconductors, coherence length is important, up to what level we can go down in size. We will not go to 7 nanometer for sure, I believe, right? But we can still go down, and we need also to do measurements, not only trust scientists in some way. Because, okay, theory is, okay, coherence length is this, we cannot go below. Let's try, let's see. I mean, there is still some coherence, it's not just sharp, right? Not working and working. So we can still reduce, but we will not reduce at the same level as semiconductor. Probably we stop at, in the best case, as what we have now, is 28 nanometer, which is already good. I mean, if you gain a factor of 100 of energy delay product with the same number of devices, that's good. So the good thing about this technology is we have a lot of room for improvement, which has been done during the last 20 years by semiconductors, but we still have to do it, and we are already, I would say, better with the same complexity.
Okay, thank you.
More questions? I also wanted just such a general question, or how to call it. People ask about the place of superconducting supercomputer comparing to quantum computer. I usually say that it could be two kinds. Yeah, first it is just there is a time gap between when we are waiting for quantum supercomputer. It is good time to develop superconducting supercomputer. But also it would be nice. It is optimistic view. I see it is too optimistic to combine both of them, to have such a processor, superconducting processor and quantum processor. But I see that there, in this picture, there of course it couldn't be combined with one cooler, with one cooling system. But the question probably, what do now the hopes, for example, for Majorana formulas and superconductivity on topological insulators? Maybe it will help to increase temperature.
Yes, that's there are different solutions which are investigated, of course. This Majorana qubit system are probably a solution. And in general, what can be done between the two electronics is to combine the qubit part with the superconducting electronic part to do, let's say, the control and readout. That's one solution. Of course, we still have the thermal problems, but much less than with other electronics, because semiconductor, you can cool them as well at 20 millikelvin, but there are a lot of studies to do. a lot of problems to solve. It will take time. Even if there is money, it will take time. Superconductors were already at, I mean, we can do easily. We designed this circuit at 4 Kelvin, but it's not a problem to design them at 25 millikelvin. It's really just a matter of design. There is nothing new. We know everything. So we could have an interfacing technology which consumes much less, then it will affect less the coherence time of the qubit part. So it's one solution, and I'm sure many groups, we started to discuss that with different groups in Germany and in Turkey as well, how to do some interfacing. I'm sure many groups will try to do that. We'll see if it works or not, but it's an obvious way.
Some hope can come.
Yes, definitely.
Last question from me. So recently we spoke about neuromorphic electronics, and actually I see that there are some activity, but it's not very active, not very active field, but there are some. And the question is there any attempts to make non-Boolean logic, neuromorphic system from Josephson junction?
Yes, there are a few, NIST has published things a few years ago, and last year, in 2018, first, and in Turkey as well, they did some first circuits. So there is some work starting with that, indeed, and we believe this digital pulse electronics is very nice for this neuromorphic, because brain works with pulses. That's also why it consumes low energy, right? The brain, it consumes about 20 watts. And it's quite, I mean, sometimes it can do things that a complex computer cannot do easily. So it's quite efficient in some way, and it's probably efficient because we don't spend energy when we don't use it. We just use pulses, and in between, when we don't do anything, we don't spend energy. So SF2 electronics, it's a pulse electronics. So we are it's easy to mimic the brain, and that's why a few groups have started. US, Turkey, I know, Germany as well, in immunology start, I think, to do. It's, so there are a few, I think it's one very nice solution to go with. This neuromorphic, we have advantages over semiconductor, definitely, to do it. Yes.
Okay, thank you. If there is no question, then let's thank